Hi, and welcome to Artificial Life Experiments. This video will be a quick tutorial on how to download and install Salis into your computer, how to start your own simulations and explore the Salis world with the help of the T-Salis viewer. I will try to make this tutorial as simple to follow as possible, but you will need to have some familiarity with Linux tools and know your way around a terminal. T-Salis is a text-based application and runs on a terminal environment. So, if you don't know what I'm talking about, first go check some of the many great Linux tutorials for beginners around the internet. With that out of the way, let's make a short recap, for all of you guys who are new to the channel. Salis is an artificial life platform, based on Tom Ray's Tierra, on which small programs, or organisms, replicate and evolve, while competing for resources, namely memory space, execution time and information. In short, Salis can be thought of as an instantiation of life, an ecosystem inside your computer, rather than a simulation of life. Besides Tierra, Salis also takes inspiration from Evita, Core Wars and other similar works. To get a more in-depth introduction to Salis, make sure to check out the first 3 videos of this series if you haven't already done so. So, without further ado, let's begin the tutorial. In order to run Salis in your computer, you'll first need to grab a copy of the Git repository. Again, I will be assuming you are using a Linux system or similar. If you are using Windows, like me, I recommend using Cygwin and installing Salis inside your Cygwin environment. Either way, whether you are on a Linux system or in Cygwin, be sure to have Git installed, as well as the GCC compiler, make, and the ncurses development libraries. We need to be able to link T-Salis to ncurses as well as have the ncurses header files available at compilation time. As I said, the first step will be getting a clone of the repository downloaded into our system. We do that by typing the following command: git clone http://github.com/paultoliver/salis. After the download is complete, let's enter the Salis directory and type in make, in order to build our application. Salis and T-Salis are both relatively small, so compilation should take just a few seconds. After compilation is complete, we're pretty much ready to go. Alright, so, let's now navigate into the T-Salis/bin directory. This is where our application is located. We can run T-Salis by simply typing in /T-Salis. To get a full list of commands, make sure to check out the README file inside the T-Salis directory. You can also check it out directly on the GitHub page. What I'll do now is guide you through the process of creating your own Salis simulation. First thing we want to do is select the size of our world. When we run the T-Salis command without any parameters, it will create a world of default size, which is 2 to the power of 16, or around 65 kilobytes. Let's say we want, however, to create a world that's larger, say, around 1 megabyte long. Well, 1 megabyte is close to 2 to the power of 20, so what we type is /T-Salis, n20. The resulting world is 1,048,576 bytes long, as noted on the memory module page. Note that, in Salis, memory size must always be a power of 2, and what we are providing as the command line argument is, in fact, the power, or order, of the memory size. Let's navigate to the world page. We can switch pages with the left and right arrow keys. Once in the world page, let's zoom out with X until the entire memory is in view. Now, we want to compile our ancestor organism into memory. Ancestor files, files with a .enc extension, are located in the genomes directory. On the GitHub repository there are currently 2 ancestor files named 55.enc and 32shifter.enc. Ancestor files are simple text files containing the instructions that make up each ancestor organism. To learn about what each instruction means, look into the main README file of the Salis repository. Also, feel free to write your own ancestor organisms once you get a feel for the instruction set. For this tutorial, we'll be compiling the ancestor organism named 55.enc. Let's compile our ancestor into 3 places in memory. Let's pick addresses 250,000, 500,000 and 750,000. We can open the Salis console by pressing C on the keyboard. Once inside the console, let's type in the following commands. C 250,000 underscore genomes slash 55.tank. C 500,000 underscore genomes slash 55.tank. C 750,000 underscore genomes slash 55.tank. The first C character stands for compile. Following is the desired address we will compile into, then underscore, and lastly the ancestor file we wish to compile. Compiling these programs into memory is not enough to get our simulation started. We also have to instantiate 3 processes in the same addresses we have selected. These processes are the actual organisms that will execute the instructions that were contained in the ancestor files. Processes, the living organisms of Salis, consist of a CPU and 1 or 2 associated memory blocks. We must instantiate 3 processes, each with a memory block of 55 bytes, into the same 3 addresses. We do so by opening the console and typing in N 250,000 underscore 55, N 500,000 underscore 55, N 750,000 underscore 55. After we're done, we can see where the 3 new organisms have been compiled in the world view, and, if we pan and zoom in, we can actually see the instructions. These instructions should match the instructions in the ancestor file we selected. So, we can see that the main memory block of our currently selected process is colored yellow. Take a look at the color table in the Salis README file to get the meaning of each color. 55.tank is an organism that has been manually programmed to copy itself, first forward and later backwards. I will try my best to give a quick overview of what our organism is doing here, as it does so. In Salis, we can step forward a single simulation step by hitting 1 on the keyboard. The first thing our organism will do is measure itself, with the help of the locks located at both its ends. The square bracket instruction means find the lock that corresponds to the following key, in this case, lowercase a, and store it on one of the 4 available registers. With some quick arithmetic, our organism calculates its length. Now it will allocate a new memory block, colored green, and then start copying each of its instructions, one by one, into this new block. Notice the interplay between the instruction pointer, colored red, and the seeker pointer, colored magenta. To learn what the seeker pointer does, make sure to check out the earlier videos of this series. In summary, you can think of the seeker pointer as an agent, which is sent by the instruction pointer into missions on faraway addresses. Missions may be to find a lock, like the locks mentioned before, to find a given amount of free space and allocate a child memory block into it, to read from some distant address, or to write into it. The seeker pointer can only move 1 byte per simulation update, and this has many important repercussions. For example, it means that an organism takes longer to read from, or write into, memory addresses that are further away from their current IP address. Furthermore, jumps into faraway addresses or searching for a lock that's located far away will take longer. The seeker pointer is also used for memory allocation. The consequence of this is that organisms can replicate a lot faster when there exists free space close by for them to allocate their child memory block. If they are forced to allocate far away, not only will the allocation itself take longer, but also the copying of each instruction, as the seeker pointer will have to travel that long distance every time it copies each of its instructions. Okay, so, we can see that our organism has finished copying itself forward, so what will it do now? Well, it will repeat the same process once again, but this time backwards. Remember, this organism is designed to alternate directions. Memory in Salis does not loop around, like it does in Core Wars, so organisms need to take this into account in order to survive. They cannot replicate further once they reach the edge of the world. By now, we can see the new child organism starting to copy itself as well. Okay, so let's zoom out completely again. We can tell the simulation to run at full speed by pressing the space bar, so let's do that now and take a look at how our 3 colonies grow. As I discussed on the last video of this series, we will later see some weather phenomena occur early on the simulation, namely storms at first. Storms happen when a mutant organism tries to allocate a memory block of huge size. As we let the simulation do its thing, let me talk about some of the changes I've made from previous versions. First, I've removed the ability to set constraints on memory block size. Organisms are now completely free to allocate, or try to allocate, blocks of any size, from 1 to the biggest 32-bit integer possible, that's 2 to the power of 32 minus 1. The allocation capacity of the world is also fixed to 50%. This means that old organisms begin to die as soon as new organisms fill memory up above this threshold. Lastly, cosmic rays are now the only type of mutation in Salis. The cosmic ray hit rate is also fixed. What will happen is that, each cycle, a 32-bit address will be selected. If that address happens to exist within the world, a random instruction will be added into it. This single type of mutation is enough to kickstart evolution and allow organisms to develop into new species. Alright, so this is all the time I have for this video. Before I go, let me just say I would really enjoy seeing some of you guys trying out this simulation, maybe writing your own ancestor organisms and letting them evolve for some time and see how they change. If you do, make sure to share your results. I have, for example, already seen 55.ang evolve into very interesting, and more complex, species. To find out more about that, make sure to check out the Salis discussion at Reddit, on the A-Life subreddit by visiting this link, also in the description. Lastly, if you enjoy these kinds of videos, and if you would like me to keep working on fun artificial life projects like Salis, please considering becoming a patron, link for that also in the description. Any small contribution will be greatly appreciated. If you liked the video, make sure to give it a like and subscribe to the channel. I'll be seeing you all, my fellow digital biologists, very soon.